we're going to move
Yes.
over to northern Greece, to Chalkidiki in northern Greece, where the ORMYLIA Foundation uses sophisticated NDE 4.0 methods for data fusion, AI, and diagnostics for recognition of art and cultural artifacts. I'm delighted to welcome their scientific director, Georgios Karagiannis, from ORMYLIA, to talk about the work that they do there.
Thank you very much, Martin. Thank you very much to all of you. This is somehow new technologies. Mainly, I think that the application is also new, not so new, I would say. It's now we are already 20 years old, but I think with the new technology and the new era of NDT and NDE4, we could probably have a very new application on this field. So what I'm going to present you is the development, what we have developed. We call it tomography, but it's a system and infrastructure in our laboratory for the non-destructive evaluation, authentication in the latest applications, and actually it's a bottom-up documentation of cultural heritage objects, portable objects or monuments. And we are using the DICOM, the Deconde format, which is the format for non-destructive testing files storage, in order to store our applications. Well, this is the ORMYLIA Foundation, which has two actions, actually, the Art Diagnosis Center here and the Medical Diagnosis. I'm talking about, I will talk to you about art diagnosis, but what I want to tell you is that we are transferring vice versa technologies from the medical diagnostics to the art diagnosis and vice versa, as I told you before. We are located in North Greece, in the area of Chalkidiki, as you can see here, with the red line. And what I'm going to say to you, to present you, is what we have done in order to facilitate our work using mechanical and robotic arms and scaffolds that are used in situ. The instrumentation softwares that we have developed or are built in-house, the instrumentation and the software, of course, not from scratch, of course. And I'm going to show you case studies of various kinds of objects and the analysis of them using the non-destructive testing techniques in order to understand mainly the data. I won't stick too much on the AI and the decoder. We will talk about decoder in the end of the presentation. And it's the main target actually in our work when we are receiving or where we are going to an object or to a monument is the identification of the material, the structural composition of it, the pathology in the whole structure of it. And thus we are using various kinds of tomographies. We are utilizing for this objective various techniques from physics, chemistry, and engineering, like infrared imaging, spectroscopic mapping imaging, ultraviolet visible and near-infrared mapping spectroscopy, ultrasonics and X-ray fluorescence spectroscopy, Raman micro spectroscopy, ultrasonic acoustic micro and tomography and microtomography, X-ray CT tomography and microtomography, and as well as electromagnetic tomography, which is the remote sensing, the well-known radar. The challenge is, for us now, we are a mobile lab. We go all over the world. You are going to see later. Is the design of an autonomous unified system as far as the acquisition and the processing is concerned that combines mechanical manipulation, multimodal, non-destructive scanning, and efficient image processing. This is a fight along our life, because each day of our work we are improving this infrastructure. Well, we have the possibility to analyze objects which has and see in dimensions the bulk, the volume of the object from micrometers, several micrometers, which is here is a manuscript of a paper. I'm going to show you results from this, what we are doing, cross-section of the paper. Tenths and hundreds of micrometers, like the paint layers of an art object, of an icon on wooden substrate. For instance, from hundreds to millimeters, from hundreds of micrometers to millimeters structures, like the ceramics. Here are ceramics from Azulejos from Portugal, from millimeters to centimeters level of analysis, like these mosaics or whatever, and up to meter level. So we are covering all the variety of the dimensions that are needed in order to document cultural heritage objects. Well, this is our infrastructure, our instrumentation. We have infrared imaging from 1 to 5 microns and 3 to 5 microns. We have various formats of ultrasonics from 32 kilohertz in order to penetrate meter, up to 250 megahertz in order to make microtomography. These are movable and portable infrastructure. We have electromagnetic waves, electromagnetic tomography radars sensing from 200 megahertz up to 4,000 megahertz. So we can make an image from a depth of 1 meter up to centimeter, 2-3 centimeter level. We have at the same time in situ diffuse reflectance spectroscopies in various formats. We have ATR spectroscopies in the infrared area of the spectrum from 1 to 26 microns. We have Raman spectroscopies in various formats, portables, and as well as X-ray fluorescence spectroscopy. And we have also our patented technologies which combine this kind of techniques, like spectroacoustic tomography, which combines infrared and ultrasonics in one probe. We have also the appropriate infrastructure in order to go to the monuments, either by car or by aeroplane, and go to make the analysis. This is the robotic scaffolds for the various modalities that we have that can be mantled and dismantled and go on site and make the analysis. I'm going to show you also videos from this later on. And this is the infrastructure for the various kind of the probes and the cameras, smaller probes and bigger probes, even bigger probes, the X-ray imaging, scaffolding in horizontal or perpendicular format. And this is one of our latest developments, the X-ray CT tomography, which can be set up in situ and make the analysis of the objects. We have linear stages here moving in order to zoom in and zoom out the object, which is located somewhere here. And we have also a rotating table in order to rotate the object and make the X-ray CT tomography. This is our screenshots from these scaffolds. I'm moving fast. What I want to tell you is that we have a big database. This is the support that we have now in order to apply neural networks, actually artificial intelligence techniques, in order to identify things, to identify information that is needed. And we have done, this is a big database, including objects, analysis from objects from the 17th century before Jesus Christ up to 21st century. I'm going to show you cases from this kind of objects. It is not only the span of the time, but also the span of the materials. We have from wall paintings, from stones, from marbles, from ceramics, from gold leaf tessera, metal coins, metal objects of various jewelry or craftsmanship, paper, manuscripts, of course, a significant database of icons, ceramics again of post-Byzantine and Middle Ages, modern ages, paintings, stamps, new icons, and new jewelry. We have done analysis all over Europe, Middle East, Russia, and in the other side of the Atlantic. And here we are research infrastructure of Europe, one of the 24 labs making such kind of a job. And now I'm getting into the devices and the techniques that we have with some specific information related to the kind of the data that we are acquiring. You know, all of you know very well the ultrasonics, the classical one, but what we are using are ultrasonics higher than, actually, as I told you, from all the frequencies, but ultrasonic microscopy or microtomography, which is a very powerful application of ours. We are using frequencies higher than 32 or 50 megahertz. So we are making microtomography, 3D structuring, making images from the 3D structure of micrometers, let's say the paint layers of a painting object. These are the probes that we are using. These are from 8 megahertz up to 250 megahertz, which results to having a resolution from 3 microns to 40 microns if we take into consideration that we have a velocity of wave propagation in this kind of materials of the order of 1,600 meters per second. What is the kind of information that we are acquiring with the ultrasonics of high frequencies? We are scanning areas from square areas or areas from millimeters by millimeters or centimeters by centimeters, can be more depending on the application. And we are acquiring tomographic information from all the materials that exist in the structure and that permit the propagation of the ultrasonic. We are having stratigraphic information. We have thickness measurement of multi-layer structures of the various layers. We have information about the initial designs under drawings of the paintings, for instance. We have the roughness on the surface as well as the various interfaces. And we are acquiring information about the elastic properties of the materials. The resolution is of the order, the later resolution, while we are making the scanning using the robotic arm and make the image, is of the order of 20 to 100 micrometers in the XY direction, while in the Z direction is very high frequency of the order of micron. The data format that we are acquiring, we have our formats, but we are storing now this format in DICOM format or deconter. The other very powerful modality, as I told you before, is Fourier transform infrared spectroscopy in various formats, reflectance, transmittance, ATR, or whatever. And what we are doing, as you can see, we are applying these spectrophotometers.
You can see.
Yes? You hear me? Yes.
Hear you fine. There was someone in the background, Georgios.
Okay. So we are set up in XYZ robotic arms in these scaffolds I showed you before, the spectrophotometer, and we are making the scanning. While we are processing and we are making the data, we are taking for each point spectra, we are providing to the user the mapping, spectroscopic mapping imaging in various wavelengths. This is a very powerful tool. You see, this is the kind of the spectra that we are acquiring. And from each point, we have a specific spectra. And in the various bands, we are producing cube images, which are revealing the reflection coefficient information, the underdrawings that exist in the materials identification, especially complementary to the other spectroscopic devices, which is the organic materials, kyrios, overpaintings, and the pendimendi of the creator. The spot size in this area is less than 1 millimeter. In this device is of the order of 0.8, actually, 0.8 millimeter, 800 microns. And we are storing the reflection coefficient signal and the mapping images in ASCII format in XYZ values. And now we are showing this also in cube imaging in the deconter format. The other modality is infrared imaging. You see, we have very powerful infrared cameras like FLIR X6900 and the Xenix with antimonite sensor from 1 to 5 microns. With this technique, as you can see, we are illuminating the object in various formats and we are receiving the reflection back. And with this technology, we can, by making scanning in the object using the robotic arms, we can make mosaicing of the image. So we're producing very high resolution images in the various areas. And these images are in very well agreement with the spectroscopic mapping images. So we can go to the spectroscopy or from the spectroscopy to the imaging in a secure way. This is a very powerful tool of our laboratory. What we are receiving from this technique, the infrared imaging technique, macro info related to the rest of the sensors of the spectroscopic. The whole object is scanned in several minutes, actually, or several minutes using the robotic arms. So we see very well that the drawings, the initial designs, the materials, the pendimendi, and we have very high resolution images We are storing in JPEG and PNG file format, but also we can store it in DICOM. The other modality is the Raman, portable Ramans with various lines in various frequencies. So with this, the same logic is we are scanning the object, we are making mapping, Raman mapping images, and thus we are identifying inorganic materials in complementarity to the FTIR spectroscopy. This is the way, the kind of the information that we are receiving. And as I told you before, we are receiving this Raman scattering coefficient, and we are identifying mainly inorganic materials in the whole structure, at least in the structure, in the levels that we are penetrating the object. The spot size is of the order of micron, of 20 to 80 microns. The other modality is UVVs, ultraviolet visible area spectroscopy, which is colorimetry actually. So we are making mapping images of the true color of the object, and thus we are creating a database of the fingerprint of the aesthetic result that the creator has achieved to have in the various kind of the art objects. Again, the same information. We have spectroscopic information, mainly on the color information and the aesthetic result, which reveals technique and schools of paintings. Actually, this is very powerful for paintings. Also in the marbles, where we have color, we have to measure the color with high fidelity, and thus reveals us techniques and the times of creation. And the spot size is of the order of 1 millimeter. X-ray fluorescence spectroscopy, the same logic. We are scanning with the spectroscope, and we are receiving information mainly on elemental analysis, complementary to the FTIR and the Raman spectroscopy. And this is the in situ installed X-ray CT tomography infrastructure, with which we are making X-ray tomographs, as you can see here, from very delicate and very small objects or big objects. This is a small object from the tombs of the Macedonian kings in Vergina. Imagine that this diameter here is of the order of less than of the order of centimeter, yeah. And here is the video from the DICOM format of the X-ray CT tomography of this small object, which has materials inside of it, metals and bone materials. You see the high fidelity and the information. You see very well even the roughness of the metallic materials without the bone, because we have extracted the bone, which has a different absorption from the metallic material. Okay, I move forward in order to go to cases. This is the software that we are developing, that we have developed. So all the modalities are controlled from the same software. So we are securing the common way of acquisition with using the robotic infrastructure, and the common way of storage and with high fidelity and accuracy, in order to be in position to make in an efficient way the fuse of this multidimensional information. You see, if this is an artwork area, here we are making imaging, so we are receiving information from centimeters by centimeters, but also we are scanning with the various spectroscopes or tomographs using millimeter spot size or less than millimeter. So in this small area of the millimeters, we are making microtomography using X-ray or ultrasonic. So we have a micrometer level information. And this kind of different information and kind of different lateral located information must be fused. Well, yeah. And imagine also that we are acquiring information from various kinds of objects, as I told you before, glass, metals, paintings, paint, marbles, as you can see in this transparency here, objects coming from excavations. So therefore they are suffering from various pathologies, and also materials, big one, macro, that we have to scan big areas compared to the small objects coming from excavations, as you can see here in the ancient theater of Thassos. And paintings, of course, again, for authenticity, which is an emerging application nowadays. Well, I'm going to show you cases. This is an overpainted icon. Initially, this icon was painted, or this one, and later on, this icon was painted above. And using the various modalities, like the spectroscope, the FTIR spectroscope and the Raman, we are taking measurement per wavelength, and also we are taking measurement using the infrared imaging. So we are fusing this information. We're using the appropriate technologies. I'm not getting into the mathematics. So you can see here the below existing icon and the above existing icon, and here is the infrared imaging, revealing the intermediate layers of the various paintings, and even the very thin film. You can see here is a gold leaf area. So the painter who painted the above existing icon applied a very thin film adhesive material in order the paint to adhere on the gold leaf. So we're receiving this reflection even from the infrared camera. That means we have a very high dynamic range of infrared camera in order to manage to have this. And you see also the various inscriptions of the above and the below existing icon, the angels here, and whatever, even the inscription in here. And also, we are in the position to make thermal imaging and reveal the information of the under existing icon using also thermal imaging, not only reflection imaging. And then I'm going here to 3D. Yeah. We are fusing the information in the DICOM file in the 3D sliced data. The same happens with the infrared spectroscopy and infrared imaging. And as you can see here, from the spectra, the various spectra scanning here the object, as I told you before, we are creating cube imaging. This is cube images here. In various wavelengths, we are receiving the reflection, which is actually is not a reflection image with the camera. It's an image, a chemical image, actually, of the different materials. You see here, while we are increasing the wavelength, we are the wavelength. So we have the chemical images, as I told you before here, where I mentioned with my mouse, with my cursor, and we are revealing the inscription that exists below in another icon in very high resolution, because imagine that this inscription is of the order of millimeters. Well, this is very important tool for us, and we are the only team all over the world on doing this job that we can penetrate thin, not so thin, but thin structures like this preparation layer here, which is a common technique that were used in order to apply overpaintings above another icon that existing. So there was an icon, there was a preparation layer which is cannot be penetrated by the infrared or FTIR spectroscopy, but it cannot be penetrated using ultrasonics, like here. So we can see the inscription behind the preparation layer, so we can see even the behind icon, even there is an intermediate layer of preparation, which is done only by us. And then we have the fusion of information. As I told you before, you can see here the spectroscopic mapping imagings, which the colors are revealing various kind of materials, fused with the icon, fused with the thermal images, and then these are fused, the IR imaging, with the tomographic information, which is the ultrasonics. So in the ultrasonics, we are making the appropriate geometrical transformation. We are applying Hilbert transformation, and we do the more or less the same on the infrared images, so we can fuse them and register them in a common file. Let's see an example of this. This is an icon. I'm showing you technologies, but also cases. Interesting. This is an icon, not an old one, but the new one of the 21st century. They came to our lab. They bring us to our laboratory because the customers were bought too many icons of them, and they claimed that eventually these icons were printed and not painted. They were not handmade. What we have done initially, we have done applied infrared imaging, and you can see the complementarity of the various techniques here. So we have seen this differentiation of the gray levels beneath the existing icon, which reveals us that in the area where we have these gold gildies, we have also very thin films of gold leaves behind, which is, we have other such kind of measurements in our database, and reveals that finally somebody has prepared by hands the substrate of the area in order to make the gold leaf, the gildies above. First point. Then we have applied spectroscopic mapping imaging, and there we have seen in various areas of in the phase. You see the phase of the sand here, which is a chemical again image, I say. In the various points we have the same spectra. This is strange. This is gonna mean that we have printing, but of course we haven't made zoom in the spectra to see very small fine changes. So we had then applied in the same area ultrasonic microtomography. And as you can see here in the C-scan and the C-scans, this is the cross-section here and here on the left and behind. This is the C-scan above and the slice while we are progressing the depth. Imagine that this is of the order of hundreds of microns. And as you can see here, this is the eye here, the cross-section in the area of the eye. So as you can see, we have grainy material. We have multi-layer structure, not fine printed. So we have a painted artwork. And as you can see, using microtomography, ultrasonic microtomography, we can see even the brush strokes, very small, fine micrometers on the surface of the object. Let's move forward. So the icon was painted. And here is a fusion of ultrasonics, image in the visible, and spectroscopies in the same object. Now I'm going to show you some application using the various techniques fastly, because we have 10 minutes. This is radar electromagnetic tomography from the work that we have done in the ancient theatre in Thassos. We undertook the task, the project, to fill with, artificial marble, to fill the areas where not the old marbles were existing. And then in order to do that, we have a special concrete design of artificial marble, and we have also applied titanium, how we call it, reinforcement inside. So we, using the radars, we are making quality check control, we are making tomography to see if the titanium and the various metallic objects inside, in order to make robust the concrete, are well applied and are in parallel to the surface. As you can see here, the cross binding metallic objects are in very well parallelization with the surface while making the scanning. While in this case, where is the other one? I lost. There was another slide where this the metallic object was not parallel, so this was a problematic case. So we are making again the filling of the marbles. This is another case, scanning behind the mortar of like what happens in Hagia Sophia or in many other churches all over the world. I'm going to show you also another example from Bethlehem. Here is the way that this is structured. So unfortunately, above the mosaics are mortars applied. So we have, using the appropriate technology in our ultrasonic linear arrays with the beam forcing and the motion planning of the transducer, as well as changing the angle in order to focus in the various depths of the tessera of the mosaic, and by applying the optimal velocity of the scanner, we can see these very nice images where we are revealing the hidden mosaic behind. See here. And this is done in very high fidelity. You can see here the C-scan. So we are penetrating the mortar, as you can see here, and we can navigate in the mosaic area in high resolution. This is a scanning in Bethlehem. This is another scanning where we have revealed, as you can see here, a mosaic behind another mosaic in the Church of Nativity in Bethlehem in the Palestinian Authority. Well, so we have the software where we can control our ultrasonics, all the dynamic rates. We can control the focus area, the depth, and all of these things, as I told you. This is the marbles that we have filled in the ancient theater of Thassos. And this is, again, this is the bad case. Here I have it. You can see that the reinforcement in the concrete is not well done. Okay, I'm moving forward. Tomography, microtomography using ultrasonics of tessera. We see the cracks. Microtomography of coins. So we're revealing the internal structure. You see here is a coin of a thickness of 1 millimeter, and by progressing the slices in depth, we can reveal the internal structure, so the restorer, the conservator, knows exactly what he's going to face, or he or she going to face while cleaning and not destroying the object. And then I move forward. This is conservation. We are applying now on also conservation of paper. And this is a very interesting case. We are the only lab that applies and provides to the customer quality check for the filling on the tier of the paper using this paper mass in order to fill the tier and therefore make more concrete, more robust the paper. So by applying in these areas ultrasonography, you see, this is the paper, and these are the areas of the fulfillment with the paper, the new paper mass, and you can see the cross section here. So we see very well that the paper mass has filled the paper, the old paper, so they have become one thing. This is another very small object. It's a glass object from the tombs of Macedonian kings. Well, there is a big, I cannot tell the story, I don't have the time, but the problem with the Macedonian kings is that in the tombs there are very fine objects of high art, and we don't know exactly how they managed to do them, to craft them, to create them. Nevertheless, this is X-ray CT tomography. We have seen the internal structure, but this is the infrared, the ultrasonic microtomograph, where here we have seen the slice of the object inside where there is a gold leaf here. This was a very important information about the creation of the objects for the archaeologist. And I tell you that this is a small time window of nanoseconds in ultrasonography, as you know, most of you, I suppose, which opens a big object, a big window in the archaeology and in the era of archaeology in the Macedonian history. Well, this is wooden objects tomography from the Church of Nativity in Bethlehem, in situ X-ray CT tomography, where we are observing the whole pathology of the whole structure, the nails and the cracks and the gold leaves where exist. Well, I have plenty of cases. I will go. This is a problem with jewelry. Our lab, we can make image on the bulk. So while we are scanning with XRF spectroscopy, we can see the very thin film of gold plate above. But what if there is no gold in the bulk, in the whole structure? Then using ultrasonography, we can identify, for instance, in this case, they were claiming that this was bulk, the bulk was gold, but it was not. We have reflection from the plate, and behind we have another metal. So I'm moving forward. This is a fake of the density study. This is the original painting of Monastery of Simonopetras, and this is the fake one. We have made infrared imaging, you can see on the right, and if you can make the mathematics, the infrared imaging initial design reveals that the design was taken from the initial painting. You see here, It follows exactly the real painting, the non-fake. And then he painted, and while he painted, he changed it totally from the design, at least in the borders area. So we can find the fake. I'm moving forward fast. No, not here. I can stop because I think, how can I make stop the presentation to okay. And I will jump to a last paradigm here. And if you want, I can run through again. Here. This is a painting that came to our laboratory, claiming that is coming from that is created from a very important painter. Indeed, it's an interesting painting. And as you can see, we are using our robotic arms. We have made very high resolution scanning using Hasselblad and the appropriate lens. So we can see this is 13 gigabyte file of the brush strokes of the painting on the ice. Well, you can see here, so we can observe very well the brushstroke of the painter. And then we applied multispectral imaging, as I told you before, UV image, so we can see the pathology or revealing information that is not seen with the eye. And we have revealed the inscription, the signature of the creator, but making infrared imaging, so we are going deeper than this, we find another painting, as you can see. And then we can see here the distractions changing of the face of the mandals. Here another thing existing, and applying X-ray, we have seen better the change of the mandals and the initial painting. And indeed, the technique of the under existing painter is very well and very near to the Salvatore Mundi technique, the well-known painting that was sold for $100 million. So what we are delivering to the customer is the DICOM file with all the information embedded on the object, for instance, the multispectral imaging. Having the information to observe the underpainting and the corresponding spectroscopic mapping imaging, the intermediate existing layers and the above existing layers with the corresponding, again, chemical or whatever related information. And this is the case of the Deconde file. We can store the components and the images and the various information about the equipment. And we can store also all the technical information related to the way that the acquisition was done. Depth of color, number of the arms that we are using, dimensions, and all of this. And all this information is actually the same. We have the object in the same format. We have the areas of the scanning or the whole object of region of interest. We have the A scans for the ultrasonic. We have the spectroscopic information for the spectroscopies. We have the reflection coefficient like the A scans in the radars. So this we are treating in the common way. And this is a blessing because DICOM gives this, Deconde gives this possibility and the opportunity to do this in our kind of data. These are some screenshots from the various missions. And this is our last mission that finished several months ago from the tombs of ancient site of HOIS, where the tombs of the Macedonian kings exist like this. You probably all know this very important, actually is the same importance site as Acropolis in Athens. And this is the bed in which Philippos II, the father of Alexander the Great, was found in the tomb. And all these objects that I show you before, these nice objects, is coming from this very delicate and high art high level of art areas of the bed of Philippos. And this is a video of our, and I'm closing here, I think, where you can see our infrastructure, most of our infrastructure set up in the area of the tombs, and we have made the analysis with these various kind of masses, how the ultrasonics are scanning or the various modalities of the objects, making all of these kind of tomographies and spectroscopies and photographs. It does not take too long, and I'm closing here. X-ray CT tomography. We have found a small head there in the mass. Actually, we are talking a micro excavation, a non-destructive micro excavation. Ultrasonic CT, ultrasonic tomography. Sometimes the robotic arms are not so useful, so we are using manual procedures. As you can see, we were focusing the object manually there. Whoever has experience from the field can understand this. So thank you very much for your attention, and I'm here for any questions.
Thank you enormously, Georgios. It's so fascinating fusion of data, use of AI, use of NDE 4.0, the way you can go through the DICON information and look at different levels and compare the multiple techniques and things is wonderful. Ikesh, would you like to ask the first question?
In your overview, majority of applications you have mentioned and the examples are mostly the laboratory in a control environment. Any experience providing all these solutions in the field condition, and are there any challenges that you faced compared to laboratory control conditions?
Yes, as I told you in the presentation, a part of them, a significant part of them were not in our laboratory. Actually, the last video is not in the laboratory of ours, it's in the laboratory of the excavation. So usually when we go to an excavation or to a monument, there is a place where we can set up and make our work in a more controlled environment. We have never faced the problem to make the analysis in situ on the soil under the sun. This has happened very few times. Usually they take the object from the excavation, they bring us nearby where there is a tent, there is a, you know, a very draft infrastructure in order to set up our instruments and make the analysis. Yes, my experience from the field, like Bethlehem or Muster in Switzerland or Oslo last month, is that in many times, these automatic procedures and robotics are not so useful. You know, you have to move manually the motor to go to a specific point and take a measurement because the archaeologist is asking you, what is this, what is that? You understand? So this very high level of automation is not so well exploited in situ in many times. That's what I can say.
Yeah. Okay.
But there are cases, of course, that we exploit this in a very efficient way, depending on the application, actually.
Yeah. You've got a very sophisticated range of different NDT techniques. How did those develop and evolve, and how do you decide which techniques you're going to apply to a particular object?
Yeah, very good question. Yeah, indeed. Well, after some years of experience, there is a protocol per kind of object. For instance, in the paintings, the first thing that we are doing after taking high resolution photographs, imaging, we are making infrared imaging in order to see if there are region of interest behind. And there, in this specific region of interest, we are applying spectroscopies. If we have a marble, we are applying firstly tomographs in order to see the internal structure in a more efficient way. So, depending on the object, there are various combination of the techniques that we are following in order to have the efficient result. But this is, made by design, I can say, taking into consideration the physics of the techniques, but mainly from experience.
Great. Thank you, Georgios. We're having time in the schedule where we need to move on. There's just a couple of questions here. One asked about the coupling of the ultrasound. Is coupling gel used, or is it out of the question for these type of artifacts?
When permitted, we can apply gel. In many cases of the icons and paintings who have varnish, we apply gel so the varnish are protecting the diffusion of the gel in the painting. But now we have developed a probe with which we are making dry intakes, dry contact. We have, we have the water or the gel in a mask in which the transducer is moving, and this mask is very adhesive. It's very soft, so it touches the object, and we are making the coupling. This was very successfully applied 4 months ago in the gallery, the National Gallery of Paintings in Oslo, in Norway. I can show you, but if we had time, we can show you results only in another presentation of this microtomography of the various layers there.
That would be wonderful another time. Carla from Petrobras was fascinated by the results and wondered whether there are some articles you could maybe put the details in the chat.
Okay, some articles of ours. No, I'm not easy. I cannot do it right now, but I can send to you.
That would be perfect.
Yes, I will send you an email to you, Martin, and you can diffuse in the community.
Perfect.
And make a selection. Okay.
Okay. Absolutely wonderful, absolutely fascinating, and I'm sure Jens Martin who's in the audience, will be very interested in how you've used Diconde. So thank you again, and we'll move forward into schedule to the next talk. And thanks for joining, particularly.
I thank you very much.